Time for some discussion about gases, their properties and behavior. Talk about an interesting photograph. There is a elephant who is apparently experiencing some distress, and veterinary assistants are attending him. And can you imagine what it would take to anesthetize one? Well, that would require some skill and knowledge with gases and their various behavior properties. Okay, well, perhaps we won't anesthetize an elephant, but let's see what other kinds of things we need to learn about for gases. Our list of learning objectives for this chapter is shown here, and for this particular recording, I'm going to talk about the elements that exist as gases at normal temperature and pressure, which may or may not have come to your notice by now. We'll look at the 4 common physical characteristics of gases. That's not very complex, but it's worth a conversation. And talk about the different units of pressure that you'll run into. It's a conversion exercise. And how the pressure of a gas is measured using a manometer. What in the world is that? Okay, so which elements exist as gases at 25 Celsius and 1 atmosphere? You may have seen this somewhere along the way as we introduced elements, but maybe not. So notice which ones here are shown in blue. The ones shown in blue are indeed those which occur as gases. So in other words, there are only so many, and they are very conspicuously in groupings, especially the noble gases. The top of the P block that includes nitrogen, oxygen, fluorine, and one other from the halogens and chlorines, and then of course hydrogen. So you need to recognize that, so when you see examples, those compounds or those elements will definitely be occurring as gases. Trivia point, now you know. What are characteristics of gases that we need to know about? Well, they are the most compressible state of matter. That makes sense. There's a lot of empty space in them. They mix evenly and completely when you confine them in a container. You can't have some of the gas one place and not another. They don't. They just mix. They will assume the volume and the shape of a container. You probably have seen evidence of things like that. And there's an example of nitrogen dioxide gas there where it's completely filling the container. And they have much lower densities than liquids and solids. Obviously, when there's a lot of compressibility, that's because there's a lot of empty space. Things to know about gases. One other aspect, and we'll come back to this eventually, is that there's very little attraction between gas particles. And that comes into our assumptions about how gases behave. In other words, we assume that they're far enough apart that they don't influence one another with any kinds of attractions. When we're describing gases, we'll talk about what's in air and various things about pressure. So the chart from the text here shows us the composition of dry air at sea level. And as is quite evident here, the major component, 78%, is nitrogen. Oxygen, we often misunderstand that oxygen is a primary component. It's not. It's a larger component, but not nearly as much as nitrogen. And then there's a lot of other smaller things that are less than 1%. Argon, carbon dioxide, neon, helium, methane, and krypton. We'll notice those last 4 are very small components, very small fraction by mass. Good things to know about that are related to air. Obviously, those all have to be gases. Gases mixtures are going to be homogeneous and they're going to be compressible. They have a large collection of particles moving randomly to a volume that is primarily empty space, which is why you can compress them. And so the collisions of those randomly moving particles with the walls of the container give you what we perceive as pressure. In other words, the force per unit area is defined as the pressure. And so collisions with the side of the container are represented here with the arrows of little spheres bumping into the sides. That's what that represents. Well, pressure is, as I just noted, force per unit area. That's a strict definition from physics and all. And there's different ways of representing and units for force. In terms of where does it come from? Well, an atmospheric pressure is what you get when you have the column of air that starts way out in the atmosphere and presses all the way down to the surface of the earth. Then you have atmospheric pressure, and that is a force times the mass of air, wow, and related to its mass times acceleration, hello. And the pressure is going to be the force per area at the surface of the Earth. Well, that's a funky definition, but we don't need to focus on it as often. We will use instead, spend time thinking about conversions. Atmosphere is our very common unit. It's the same thing as millimeters of mercury, which is related to a device we use for measuring pressures. You'll see that soon. There's another one called torr, which is the same thing as millimeters of mercury. There is the bar, which is used in weather reporting often. And then there's pascals, which is used, it's the SI unit that if you went to Winnipeg and you listened to the weather report on the news, they have pressures reported in pascals or kilopascals. And the relationship to atmospheres is shown here. These numbers are kind of odd, but you'll get used to them, and you can look them up when you need them. All right, so what's next here? Okay, force is mass times acceleration, but we don't need to use that direct definition often. When we're measuring pressure of a gas to represent how much pressure there is, it's going to be related to atmospheric pressure. And the downward pressure of the mercury in the column, in that tall skinny tube there, is going to be balanced by the outside atmospheric pressure that presses down on the mercury in the dishes and pushes up the mercury in this column. So if you're at ordinary atmospheric pressure, that's 760 millimeters of mercury, in fact. And so we can relate the atmospheric pressure to the height of a column of mercury. In this device we call a barometer. The units for pressure that we will run into again are Pascal, which is PA. I guess it doesn't look like Pascal, does it? Maybe I'll write that in for you. Pascal is abbreviated by PA. Torr is an abbreviation for someone's name, but you're not responsible to care who that would be. Millimeters of mercury relates to the barometer, and these two units are in fact the same size of a unit. 1 torr is 1 millimeter of mercury, and atmospheres relates to ordinary pressures in the atmosphere. And then the other one is called a bar. So you'll see those from time to time. Look them up if you need to make conversions. It's again an exercise in mathematical conversions between different units. All right, so atmospheric pressure is the pressure that's exerted by the Earth's atmosphere. Think about that again for a second. At sea level, essentially you have 1 atmosphere is the normal pressure. If you go up higher, 4 miles, for example, you get about half as much pressure. If you go up 10 miles, you're down to 2.2 atmospheres. In other words, 20% as much, 1/5. And when you get way out there, far away, you'll be even less, not absolute pressure, but very, very low pressure when you get out. So barometric pressure relates to the column of air that is experienced at any one spot, say here in our local faces, what column of air is pressing on us, and that barometric pressure relates to the density of the air in the weather systems that we have. All right, to measure gas pressure, the barometer is used, but sometimes we'll compare the pressure of a gas in a closed flask, such as is shown in this device here we call a manometer. A manometer is used to measure pressure of a gas in a closed container, like we're seeing on this diagram here. And it's you have a valve at the top here. The valve allows the gas to be in contact with our tube of mercury. That's the typical thing used here. And yes, mercury is hazardous to work with, but it's what's used in these devices commonly. And when you open the valve to the mercury, be in contact with the mercury, the gas, whatever pressure it is, will push against the mercury, and it will be a comparison of how the pressure of the air outside this open-end device is pressing on the mercury compared to that pressure of the gas. So in this example, the pressure of the gas is less than the 1 atmosphere of the outside, the part that's open to the air, because the height of the mercury is higher on the side with the gas. That's because the pressure of the gas is less, and the pressure outside is more than the one of the gas. On the right side is the opposite situation, where you have the pressure of the gas is greater than the exterior pressure of 1 atmosphere. And so in this case, the pressure of the gas is pressing more forcefully, if you will, on the mercury, and forcing the level of the mercury to be less high, or higher on the side that's open to the air, so the outside air is less pressure than the gas, so the pressure of the gas in this case is greater than the outside in this is labeled to be 1 atmosphere. So if you can interpret these diagrams, if you understand what is pressing against, remember this is liquid mercury in the device, that gives us a way to relate the pressure of the two things. So what do we use it? How do we use it? So you can use a manometer like this to determine the pressure of the gas, knowing what the outside pressure is for this situation. So in this case, it's not labeled on the diagram. I'm going to move my icon here. And it tells us that the outside pressure is 750 millimeters of mercury, so that's what's here, 750, pressing against the mercury literally in those units. And then the pressure of the gas is pressing against the opposite side. And in this case, the pressure of the gas, is it more or is it less? So the pressure of the gas, we have to think about it. This is a logic problem. Sometimes people find these a little puzzling. The pressure of the gas is pressing down to this level. In other words, it's pushed farther down than the side from the exterior, open to the air. And so the pressure of the gas is greater than the pressure outside in this case. And we'll have to figure out how much greater. Well, this is related to a mercury manometer. So we're going to literally be looking at the height of the difference, the column of mercury difference between the two. And so the pressure of the gas is going to be greater than the outside pressure, but it's going to be something greater than the 750. So we're going to add to it a height of the mercury. So 750 millimeters of mercury. We'll have added to it the height of the mercury, which is 23 centimeters. Wait a minute, 23 centimeters, that's not going to be the right units. So 23 centimeters is the same thing as 230 millimeters, if you remember how many millimeters are in a centimeter. Then centimeters of mercury, that works, or sorry, can be converted to millimeters, and then we will have units that are consistent. And now it's a simple math problem to add them together to determine the pressure of the gas in this case, certainly greater than the outside, but sum of those two values gives you 980 millimeters of mercury. This one is greater in this example. The pressure of the gas that's green in that picture is greater. You can tell because of the greater influence of that gas pushing the mercury down on the left side of the manometer. You need to get an idea how these work. They take a little bit of thinking, but they're not so bad. Okay, so we could do another example or two. We'll try not to make this complex because I'm not using my usual device to write the problems out. If you go up on the mountain and you go to someplace like Pikes Peak and the atmospheric pressure is low, as one might know, how do we convert these to different values? So 480 millimeters of mercury, how do you relate that to atmosphere? Well, you go back a couple of frames and you find the conversion tools, and 480 millimeters of mercury is going to be what? Okay, for an expedient explanation here, there's the rest of the pieces you need to see. So starting with your 400 millimeters of mercury, you need to know the conversions. 1 atmosphere is 760 millimeters of mercury, and that comes out to be 0.632 atmosphere, in other words, less than 1 atmosphere. And you can take that same value and calculate the number of pascals, because there's 101,325 pascals per atmosphere. It gives you a big number. Pascals are always big numbers. And if you wanted to know torr, well, it's always exactly the same as millimeters of mercury. Okay, this would be enough for the first section of this chapter. I hope this is useful to you. Don't forget to pay attention to the details. Please ask more questions as needed. And good luck on your homework. See you in class.